All right, hello everyone. I'm joining you from the middle of the action. We're already in orbit around the Earth. So we're sort of at a medium distance right now. We're not already at the moon yet, but we're definitely not super close to Earth either. So we're sort of in between. Now you might be thinking right now, that's an incredibly stylish rocket. I wonder who designed that. And I, in fact, built the rocket myself. So I think some credit is due there. But that's not the only thing that's special about this rocket. Not only is it incredibly fashionable, but it also happens to have infinite fuel. NASA said it couldn't be done, but I guess NASA was just wrong. I guess I'm just a little bit better than NASA, if I'm going to be honest. So we're just going to point directly at the moon. I'm sure everything will go... Okay, that's definitely not what's supposed to happen. I had absolutely no idea this would happen. Who could have expected it? Definitely not me. That we would end up going left. Even though we're pointed at the moon. It just doesn't make sense. You know what? I'm sure it was a computer error. You know? Computers have glitches all the time. It says we're going to end up in orbit around the sun, which doesn't make any sense at all. You know? So we're just going to we're going to speed up the footage a little bit. We're going to make sure because I'm sure that the computer is simply wrong. I'm sure we are going to reach the moon and that our trajectory is wrong. So it seems like the computer was in fact right. So we did miss both moons. And it's actually kind of impressive how we missed both moons. You seem like we were almost guaranteed to hit one of them, but we kind of thread the needle there. And our astronauts are going to spend eternity in space. So you guys can clearly appreciate the stakes here. You guys can see how important it is to know the basics of orbital mechanics. Okay, this first section is going to be a super quick review. So obviously orbits are elliptical. The point that's closest to the planet, you're going to be traveling the fastest, and the point that's furthest, you're going to be traveling the slowest. This is because you need to conserve mechanical energy. You have higher potential energy, it means you need to have lower kinetic energy. The highest point in your orbit, which means also the slowest that your vessel is going, is called the apoapsis. And the periapsis is the lowest point, or the fastest that you're going. As you can see, the lower that you get, the faster that you go. And then you get higher up, you slow back down, just like on a roller coaster. You're trading potential energy for kinetic energy and then trading it back for potential energy. And that is all that you need to know. That's a super quick overview of elliptical orbits. Now we can move on to basic orbital maneuvers. When we talk about orbital maneuvers, it's basically just a fancy word for saying accelerating in a direction in order to change our orbit. So there are going to be 6 important directions to remember. The first is prograde. It's the simplest. It's the direction of velocity. It's the direction that your rocket is going currently. So if you burn prograde, if you accelerate your rocket in the direction of your velocity, you're going to extend the opposite side of your orbit. As you can see, the arrow is pointing towards the direction that we're accelerating, and the opposite of prograde is called retrograde. And retrograde is pointing away from the direction that you are moving, that your rocket is moving, and it's going to lower the opposite side of the orbit and give you a lower periapsis. This is simply just to show which direction the rocket is orbiting. The next important direction is going to be radial out. So this is pointing away from the center of the ellipse. There will be an arrow showing the direction that we're accelerating soon. it's going to be pointing outwards away from the center of your elliptical orbit. This one's more circular, but it's basically going to shift your orbit. It's going to be directly counteracting gravity, so it's just going to shift your orbit. It's not going to make it bigger or smaller. As you can see, it's more elliptical, although it's the same size. Going to burn a little bit more just to make it a little bit more obvious how the orbit's changed. And remember that these orbits are all counterclockwise. So just to make sure that you know which direction we're going, it's always going to be counterclockwise. And of course, the opposite of radial out is obviously going to be radial in. So we're just going to reset to a circular orbit again. And now we're going to burn radial in, which will do the exact opposite. It will shift our orbit, but in the opposite way. It's really hard to describe with words exactly how it's changing, so you sort of have to just let the video do the talking. Same size of orbit, it's just going to make it more elliptical. Now that we've finished our burn, we can move on to the final direction that's important. It's going to be normal and anti-normal. And these are going to be perpendicular to the orbital plane. It's going to be how we change the inclination of the orbit. So it's going to make our orbit more inclined. As you can see, we're pointed straight upwards. We burn straight upwards, and it will change our inclination. This is used more than you would expect. Radial in and radial out is pretty rare. Prograde and retrograde are the most common, but every once in a while you will need to burn normal and anti-normal just to match the inclination of a target that you're trying to dock with, or maybe you're trying to head over a specific region in the north or south, so you need to head on an inclined orbit. Obviously, in order to get back down, we have to point anti-normal, and it's going to basically undo everything that we just did. It's going to take our inclined orbit and it will level it out. And those two directions are how you do inclination changes. So together, those six are the common directions for your reference frame. Since you're in space, you don't necessarily have a reference frame. You use your velocity and orbit as a reference frame. So we just got a graphics upgrade. I just noticed that. I forgot to activate the filters that make it look better. So huge upgrade, and just in time, because the next thing that we're going to do is a Hohmann transfer. So this is to lower to a circular orbit that's smaller. So the way that we do this is to burn retrograde once, and then we're actually going to need to do a second burn at periapsis. So we lowered the other side of our orbit, and now we need to do a second burn to circularize at a smaller orbit. So we're going to head over to the other side. I went a little bit too far that time, so I'm going to actually complete another orbit just because I kind of overshot it. You want to do it at the lowest point. Gonna slowly inch towards. That looks good enough. Now we're going to do a second burn retrograde to circularize our orbit. As you can see, we went from a higher orbit down to a lower circular orbit. So the next step would be, how do we get into a higher circular orbit? Well, we can do another Hohmann transfer, but instead of burning retrograde to make it smaller, we can burn prograde to make it bigger. So just give our second for our rocket to flip around. It's kind of dark, so you can't really see, but our rocket is basically turning to point prograde, and we're going to do a burn to extend our orbit outwards. Once we're happy, once our orbit intersects our target circular orbit, this is called a Hohmann transfer orbit, just because it's sort of like an in-between. We're heading all the way outwards, and once we're at our highest point, we're going to point prograde again, and we're going to do a second burn to circularize in deep space. As you can see, now we've went from a medium orbit down to a small orbit, and then back out to an even larger orbit using Hohmann transfers. And that concludes our basic maneuvers. Now, the important thing is going to be optimizing our maneuvers to make sure that we're efficient with our burns, because we don't want to be wasting fuel if we don't have to. So this is going to be optimizing fuel expenditure, or optimizing the delta V that we use. So you're probably wondering why I'm showing you a picture of this plane right now. I thought we were talking about rockets. Well, first of all, there's a couple reasons. First, I'm getting my pilot's license. But more importantly, planes have a range, right? Planes have a circular range in kilometers or miles if you're American. But basically, they have a range that's measured in distance. While rockets, they also have a range, but it's actually measured in delta V, or how much they can change their velocity. That's sort of their measurement of range. So you want to minimize the amount of delta V that you use up, because your rocket has a set amount of change in velocity, and you want to minimize the amount that you use on each burn. So that's why it's important to optimize these burns, to perform these burns optimally. So let's take a look at the first example. First example, oh wait, I completely forgot. Okay, there's a lot of things to talk about. First of all, we're performing a burn right now. We're going from a highly elliptical and inclined orbit, and we're doing 2 burns to lower it, just to see how much it costs. So that basically just fidgeting with it, just making sure it's about as good as I can get it without trying too hard. That took about 1,265 meters per second of delta V to go from that orbit. Now we're going to reload it. We're going to go to the exact same orbit that we were in before, and we're going to try and do both burns at once. That's what this maneuver node planner is, what it's called. It's going to basically show which direction you have to burn in order to do both the inclination change and the circularization burn at once. Just fidgeting around. And it takes about 30% less fuel to circularize if you only did it in one burn. So why is this? Well, the reason is just because of the way the vectors work. So if we look at this, when you're doing it in 2 burns, it's actually incredibly inefficient. You're doing one normal burn to level it out, but then you have to do another burn to lower your velocity. Whereas you can just do both burns at once, and it's a much shorter path, and it's going to be much more efficient with your fuel. So that's why you always want to try and do things in one burn. You never want to do 2 unless you have to. Well, never is actually a strong word. You probably shouldn't. The next part of optimization that we're going to talk about is just that it gets easier to extend your orbit the farther out it already is. So we're still firing our engines at 100% thrust. We're accelerating at the same rate. But you see, it becomes exponentially faster how far our orbit extends based on how far out it already is. So here's sort of like a math breakdown. So to go from the orbit of the ISS, which is the blue, to the black orbit, which is an orbit that's been extended out the distance of the moon, which is about 400 million meters, it takes 3,000 meters per second of fuel, which is only about 30% more than it would take to go 1/10 of that distance. So it still takes 2,500 meters per second of delta V to go 1/10 of the way to the moon, just because it gets exponentially easier. So here's sort of like the reasoning behind that. If your apoapsis is in a place with 10 meters per second squared of gravity, and you burn 10 meters per second radial out, it only takes 1 second for gravity to cancel that out. But if you're at a point where gravity is 1 meter per second squared, and you add that same 10 meters per second radial out, it'll take 10 seconds for gravity to cancel it out. So the further out you are, the weaker gravity is, the longer it will take to get rid of any energy that you put into it. This is editing, Kyle. I kind of forgot about one of the most important parts. This is called the Oberth effect, and it's basically saying the faster that you're moving, the more efficient your burns will be, because the payload holds on to excess potential energy that it doesn't have at periapsis. So you want to make your burns at periapsis for retrograde and prograde. Unlike the retrograde and prograde burns, when you're doing radial in, radial out, normal or anti-normal, basically any direction besides retrograde and prograde, it's actually going to be more efficient to do it at apoapsis rather than periapsis. Here's a little demonstration, basically just the computer showing how much delta V it would take to perform this inclination change. Basically just fiddling with it until it looks about level. So it takes about 1,125 meters per second to perform this inclination change at periapsis. So let's just compare that, because that's a pretty large burn. That's a really expensive, costly burn that you likely would not want to do. So let's compare that to what it would look like if we did that burn at apoapsis, if we did that inclination change. As you can see, at apoapsis, it only takes 150 meters per second. So way less delta V to perform it at apoapsis compared to periapsis. So it's not like the prograde and retrograde burns. You want to do every other burn at the farthest point that you can. This simply because when you're going from one velocity to another, basically when you're performing an inclination, you need to change it a certain number of degrees. So it's as simple as if the vectors have a smaller magnitude, then it's going to be easier to change their direction. It's pretty intuitive actually when you think about it, but you probably wouldn't think of it unless someone specifically brought this up to you. That pretty much wraps up everything for optimization. Now we're moving on to orbital rendezvous. So basically just trying to get intercepts with planets or trying to dock with a space station. Speaking of which, here's our first example. We're currently orbiting Earth and we are slightly behind the space station. So the first thing you'd probably think to do is to burn prograde, because you'd want to try and catch up to it, so you'd accelerate in its direction. See, we're pointed directly at it, so we might as well fire our engines and try and catch up to it. But the counterintuitive thing about rendezvous in orbit is that this is actually going to be counterproductive. If we speed up time, we see that although we're going faster than it right now, after one orbit, we'll actually end up behind it because we've raised our orbit, which means it's going to take longer to complete. So after this one orbit, we're actually going to end up even further behind than we started if we try and fire our engines towards it. So let's redo that scenario. But instead of firing our engines towards it, we're going to fire our engines directly away from it. We're going to burn retrograde very slightly, lower our orbit so that after one revolution around the planet, we'll hopefully have caught up to him. So that's a very, very, very small retrograde burn. It's very hard to see, but our orbit is very slightly smaller than the space station that we're trying to catch up with. So if we accelerate time, we can see that we are, in fact, not getting further away like before, so that's a good start. Again, accelerate time faster, and you can see that we are actually catching up to it. We aren't quite caught up after one revolution like what we hoped for, but we can simply do another revolution around the planet to try and catch up to him. Without doing the math, it's kind of trial and error. But you can see, after our second revolution around the planet, we've essentially caught up, and it's actually close enough that we can barely see it off in the distance, the space station. So now that we have caught up to it, now we're going to raise our orbit at the same point that we lowered it, just to match the space station's orbit exactly. So we will be stationary relative to it. So very slowly, it's difficult to see, but slowly we raised our apoapsis to match the same height, and now, just like that, we've essentially done an orbital rendezvous. Of course, we haven't hit it. That requires a little bit more precision than we can get, but you can see that we are not separating from it. We're still really close. The next part is actually quite a bit simpler. The first part was rendezvous with other satellites. Now we're trying to rendezvous with a planet with its own gravitational pull. So there's no real exact way of eyeballing how far you want to lead your target. That's sort of something that you need math for, but basically just trial and error, you'll eventually get it. You can see basically you just want the periapsis on your flyby. You're flying by it, you're going to enter its sphere of influence and leave it. You want the periapsis to be as low as possible because of the over-Earth effect. We're going to burn retrograde to get a lunar capture, turn our lunar flyby into a lunar capture. So we're going to want to maximize how fast we're traveling when we perform that retrograde burn. So as you can see, all we had to do was extend our orbit to an intersection. And then we're going to enter the moon's sphere of influence. So we're no longer orbiting Earth at the moment. We're orbiting the moon temporarily. But as you can see, we're on an escape trajectory. We're going too fast, and we're going to actually leave the moon's sphere of influence. So we need to lower our orbit, because this is an ellipse, but it's cut off. So we have to lower the ellipse to within the moon's sphere of influence by burning retrograde at periapsis. Right now, we're going to turn our rocket now that we're pointing retrograde, we're going to lower it, and now our ellipse is within the moon's sphere of influence. Now we've turned it into a lunar capture, and that's how you rendezvous with a planet. You can see that it's going to stay in the moon's sphere of influence no matter how much time passes, because I think there's a good opportunity to talk about the simulation. It only simulates the effects of the gravitational dominant body. So it only calculates the force of one object at a time, just for the sake of simplicity. So that was my least favorite part, rendezvous. This next section is without a doubt my favorite part. It's called gravity assists, and it's essentially using planets to slingshot your spacecraft faster. So we need to look at this from two separate frames of reference. We need to look at it relative to the sun and relative to the planet that it's orbiting. The planet that it's orbiting will be moving in a higher orbit, so we'll say it's moving at 100 meters per second because it's a higher energy orbit, while the spacecraft is moving in a lower energy orbit, so it must be moving slower at 10 meters per second. That means it's moving 90 meters per second relative to the planet. And because of conservation of mechanical energy, we know it's always going to end at the same velocity that it started with, of 90 meters per second, but in a different direction. It's also important to note that the planet is still moving. So even though it seems like the velocity didn't change relative to the planet, relative to the sun, we went from 10 meters per second to 190 meters per second of velocity without using any fuel, just simply using gravity. In reality, the relative velocities are almost never going perfectly left and right, so we can figure out the velocities relative to the sun and how much it changed by simply adding the vectors together, adding the velocity of the planet and the relative velocity to figure out the true velocity. Now that we sort of know how gravity assists work, we can actually try and attempt one. So this is around Jupiter because it has a lot of moons. Not exactly Jupiter, it's only about 1/7 the scale. But essentially we're going to be trying to enter a high circular orbit around Jupiter. But that's extremely expensive because Jupiter has a massive gravity well. As you can see, it's taking forever to just raise our apoapsis, even like the smallest amount. So we will be trying to get a capture with the third ring, the third moon, because it is very large and it has no atmosphere, so it has an extremely large gravity well that we can exploit and use to slingshot us into a higher orbit around Jupiter. Now right here it actually worked a little too well because it's going to slingshot us all the way outside of the Jupiter system. So what we're going to do is we're going to burn retrograde to undo the change that we just did. Just try and lower it into a circular orbit that's high above Jupiter, but that doesn't put us on an escape trajectory. That seems roughly what we want, sort of like a high orbit. It is somewhat elliptical, but that's a trade-off that we sort of just need to make. We don't really have a say in that. So I skipped ahead a little bit just because I was finding some numbers. And right here I noticed that we're actually going to collide with the planet. Our trajectory was going directly through it. So I did need to do a little bit of a correction burn, just make sure that we were not smashing into the surface on the way by. It's always important to check just to make sure. I skipped ahead just because I was finding out some numbers just for my own calculations. I didn't want to bore you guys with that. Skipped ahead to the actual gravity slingshot itself. And as you can see, it's exactly like in our simulation. We're going much slower than the moon is. We're heading at about 800 meters per second at our apoapsis, while the moon is traveling at 2,000 meters per second. So relative to the moon, we're going to be moving at 1,200 meters per second. Now we're entering its sphere of influence. So we're now orbiting it temporarily. And you can see it's going to redirect our velocity from our relative velocity from going directly against the planet's velocity to going perpendicular to it. So it will slingshot us just because our relative velocity is no longer fighting it, but it also isn't a perfect gravity assist because we only about change it 90 degrees. We don't change it the full 180. And as you can see, it worked pretty well. We ended up in a high orbit. It's elliptical, but that's not the end of the world. At this point, you guys are probably tired of hearing me talk, unless you aren't, in which case you're free to ask questions, which I am required to answer, so you will get my best answer. But anyways, to test your knowledge of orbital mechanics, I have a link on screen. And I do recommend clicking on the settings button in the bottom right, and you navigate to trail settings. Click on ellipses instead of trails because it just makes everything easier to visualize. And I recommend trying out this mission. Try and get 2 gravity assists that will slingshot you in either an extremely high orbit or to escape the solar system entirely. So that's the end of the presentation. Thank you for listening.